Howdy class. So today we're talking about section 9.6. So I'm going to start with gravimetric analysis. Gravimetric analysis is a type of quantitative analysis used to determine the purity or composition of a sample by reacting it with an aqueous solution in excess in order to form a precipitate. The precipitate is isolated and weighed to determine the mass of the desired element that came from the original sample. So this is pretty similar to this is pretty similar to combustion analysis, where we look at the masses of our products to determine the composition of our original sample. So we call this a quantitative analysis because we are calculating this percent composition using masses, so using measurable units. And we do this. So the way that we do this is that we react our sample with a solution in excess so that we know that our product is limited by the sample that we started with, so that we want to make sure that our limiting reactant is the sample that we started with, because that's the amount that we want to be able to determine by working backwards. So we have to have the other reactant in excess. And we want this to be a precipitation reaction because we want our product to be a solid so that we can isolate it from our aqueous solution. So if our product is a precipitate, it's a solid, it will crash out of solution. That's a term that we like to use in chemistry. And we will know that all of the ion that came from our original sample is in that precipitate, that there isn't any left over in the aqueous solution because we used up our limiting reactant and all of it has been converted into this solid precipitate, which we can then isolate and weigh, which you did in lab this week. Actually, you were isolating and weighing your precipitate, and you were using so in that case, you were using the precipitate to determine the percent yield of your reaction and the limiting reactant. But in this case, we know what the limiting reactant is. We make sure that it's the limiting reactant, and we isolate by vacuum filtration or some other type of drying. We isolate our precipitate and weigh it. So we get the mass. And then we use the percent composition of our precipitate to determine the mass of the desired element that came from the original sample. So this is kind of like what we did with combustion analysis. We used the carbon dioxide with the water to determine the mass of the carbon and the hydrogen that came from our original sample. Now we're doing this just with other generic elements in ionic compounds. So when we have the mass of our desired element that came from the original sample, we use that along with the mass of the original sample as a whole to determine the percent composition of the original sample. So there's two reasons we might want to do this. From this percent composition, we can identify or determine the identity of an unknown sample by its percent composition. So percent composition of ionic compounds is pretty unique to the ionic compound. So the percent composition of chlorine and sodium chloride is distinct from the percent composition of sodium or of chloride in silver chloride, for example. So they have a distinct percent composition, so that can help us to identify an unknown sample. Or if we know what the sample is, we can use this percent composition and compare it to what the ideal percent composition is of the pure substance in order to determine the purity of our sample. So we can either identify an unknown sample or determine the purity of a known sample. So this is very useful in environmental chemistry and environmental analysis. For example, an environmental sample, like a soil sample or a water sample, might contain a mixture of compounds, which we can analyze for a single compound or a single element even, by isolating the compound of interest and using gravimetric analysis to determine the amount of that compound or element in the sample. So sometimes we want to know how much of something is in a sample. Like we might want to know how much lead is in our water, because lead in your water is really bad. Lead poisoning is a really bad thing. So we might want to know how much lead was in there. Hopefully none, but probably a little bit, um, by using gravimetric analysis to examine our environmental sample. This type of analysis uses stoichiometry and percent composition to determine the purity of a chemical sample or the chemical composition of an unknown sample. So we're using percent composition for the most part, but sometimes you can also use stoichiometry if you know what the compound was that you started with and you want to know how much of that compound is in the sample, you can do that using stoichiometry. But we're going to stick to the percent composition method that they describe in your book. So here's an example. Percent composition of copper 2 plus ions in the water, which is discharged from a certain industrial plant, is determined by adding excess sodium sulfide to solution or sodium sulfide solution to a 1 or 0.1274 gram sample of the water. So this sample of water also contains sulfate ions. So we can presume that there is some copper sulfate, aqueous copper sulfate, which has dissociated into copper ions and sulfate ions in our water sample. So we're going to react our copper sulfate with sodium sulfide in order to form this precipitate, which is copper sulfide. So this is the basics of gravimetric analysis. We want to know how much copper was in our water, so we are going to react it with another aqueous ionic compound in excess in order to determine how much copper ends up in our final sample, ends up in our precipitate, which will tell us how much we started with. Because if it is our limiting reactant, then all of the copper in copper sulfide came from the copper in copper sulfate. So it's our limiting reactant. We will have more of this left over, but that's okay because we don't care. We're not trying to analyze this. We're trying to analyze this. All right, so we want to write the net ionic equation and calculate the percent composition of copper 2 plus in the water sample if we find out that we were able to form 0.0177 grams of solid copper sulfide. All right, so net ionic equations, this is a good review for you guys. Net ionic equations, first we want to write out the full ionic equation. So total ionic equation, molecular ionic equation, I forget how they say it in your book, but we're gonna break these things down. So if it's aqueous, then that means that it dissociates in solution. It is soluble. So we're gonna end up with, we have a subscript of 2 on our sodium, so we need 2 sodium plus ions. Those are aqueous. Aqueous. And this sulfide ion then is a 2 minus ion, and it's aqueous. Then our copper is 2 plus, and it's aqueous. And our sulfate is 2 minus, and it's aqueous. So those are our reactants. And then on the other side, our products, we have copper sulfide, which is a solid, so we cannot break it down. It is insoluble. It does not ionize it stays as copper sulfate. And we have, again, 2 sodiums from our subscript. That's aqueous. And another sulfate, 2-, which is aqueous. All right, so when we write our net ionic equation, we want to get rid of our spectator ions and just have the ions that form our solid product. So we look for the things that are the same on both sides of our equation. 2 sodium ions are the same on both sides of our equation. Sulfate ion and sulfate ion are the same on both sides of our equation. So our net ionic equation is Cu2 plus, which is aqueous, plus sulfur 2- sulfide ion, which is aqueous, forming CuS solid. That is our net ionic equation down here. So it's a 1-to-1 reaction. We don't have to worry about any kind of stoichiometry. But now we want to calculate the percent composition of copper based on the fact that we formed 0.0177 grams of solid copper sulfide. So let me erase my slide here so I can start over with the numbers. Okay, so copper sulfide. Copper sulfide, let's see what its molar mass is first before we do anything else. So our first step is to find the percent composition of copper in copper sulfide in our product to determine a mass of copper that came out of this product. So our molar masses of copper and sulfide are 63.546 grams per mole from copper and 32.065 grams per mole from sulfur. And if we want our percent composition, there's just one of each. There's no subscripts, so it's just one of each. So 63.546 grams per mole of copper out of our whole molar mass, molecular weight molar mass, gives us 66.463%. So there's a times 100 over here to make it a percent copper in our copper sulfide. So that means that if we were able to isolate 0.0177 grams of copper sulfide and we multiply it by the decimal version, so 0.66463, so that's the percent copper. That's going to give us, let's see, 1.0177 times 0.66463. So there is 0.011764 grams of copper in this amount of copper sulfide. Okay, so now we have a mass of copper and that all of that copper that's in here came from here. So we had 0.011764 grams of copper in our original sample, and this was the mass of our original sample. So we use the mass of copper divided by the total mass of the sample to find the percent composition of copper in the water sample. So I'm just going to erase again so that we can see everything. So I want to use 0.011764 grams divided by 0.1274 grams times 100 to make it a percentage, and that will give us 0, so it'll give us 0.09, but the times 100 part will be 9.23% copper from our water sample. That is how much copper ion is in our water sample. And you guys will see a lot of copper this week in lab, so this is just a little teaser for you, I guess. But I'm going to stop here, and then we'll talk about titrations.